So the big takeaway from the previous video, which admittedly got a little bit confusing, was that if you have the unfactored form of a polynomial, like we see written here, you can come up with this list of the possible rational roots of that polynomial. Essentially, all you do is you take the leading coefficient, 2 in this case, and the constant term, 12 in this case, and find all the factors of those two numbers. And then possible rational roots are just quotients of one of these numbers and one of these numbers. To put things a little bit more succinctly, the rational roots of a polynomial are always of the form p divided by q, where p is a factor of the constant term, so 12 in this case, and q is a factor of the leading coefficient, so 2 in this case. In other words, take any of these numbers, divide them by any of these numbers, tack on a plus and minus, and you have all of the possibilities for rational roots. And while that might seem like a positive step, we didn't really go any further than that. So we still haven't shown how we can come up with the actual roots of a polynomial. All we have right now are these possibilities. So kind of where do you go from here? Well, that's what we're going to get into in this video. The basic idea is that you got a couple different options. If you have a list of all the possibilities for rational roots, we can just take each one individually and plug it into the polynomial. So if I take my polynomial here, f of x, and evaluate f of 1, all I got to do is figure out, is this 0 or not? Well, let's see, 2 times 1 to the 4th power minus 13 times 1 cubed plus 25 times 1 squared minus 8 times 1 minus 12. That's 2 minus 13 plus 25 minus 8 minus 12. And I don't think that's going to end up being equal to 0, because I kind of have more negative, the 8, the 12, and the 13. That gives me, what, 33? Then I do positive, where I just have 27. So this does not equal 0. What does it equal to? Really, I don't care. All I'm trying to figure out is 1 a root of this polynomial? Well, if it's a root of the polynomial, it's an x-intercept of the polynomial. And if it's an x-intercept of the polynomial, its height is equal to 0. So 0 would come out. The fact that 0 is not coming out tells me that it's not a root. I don't care about its height otherwise. So I can kind of cross 1 off my list. And I could continue in that fashion if I wanted to, but it's going to be really annoying. Tedious is the way I put it over here. If we took the time to evaluate f of 2, it would be a lot of work, but eventually we'd see that 0 comes out and we'd be really happy and we'd be like, we got one of the roots of this polynomial, but we'd still have work to do. Our goal isn't to find one of the roots of the polynomial, it's to find all of them. So imagine how long it would take to plug in all of these different numbers, the positive and the negative versions of each, especially if you don't have a calculator and now you're dealing with fractions and stuff. It would be really, really tedious. And it's actually even worse than that. This only finds the rational roots, the roots that you can write as a fraction. There could be irrational roots, like the square root of 2, for example. More on that later. The point is just this isn't going to be a very efficient method for us to figure out our roots. So what are we going to do? Well, we're going to use polynomial long division. I'm guessing when I say polynomial long division, you're like, I don't know what you're talking about. So let me show you what polynomial long division is real quick, and then I'll show you how we can use polynomial long division and the concepts that we developed in the previous video to find all of the roots of a given polynomial. So first, to be able to do polynomial long division, you have to remember long division, something that you probably learned back in the day, but you may or may not remember. So let me remind you how to do long division. If you were trying to take the number 627 and divide it by 5, one way you can do that, one algorithm, is to kind of write things this way and then work from left to right. Figure out how many 5s you can get into this 6 right here. I can get one 5 into this 6, so I put a 1 up top, and then I take that 1 and multiply it by this 5 to create a 5 down here, and then I subtract. 6 minus 5 gives me 1. I bring down the next column, this 2 right here, to get me a 12. And then I repeat. Now instead of figuring out how many 5s go into 6, I figure out how many 5s go into 12. Well, let's see, I guess I could get 2 of them in there because 2 times 5 is 10. And then from this 12, I subtract this 10 and get a 2. And I bring down the next column, a 7. Then I repeat again. I try to figure out how many 5s I can get into not 6 or 12, but 27. Well, let's see, I could get 5 in there because 5 times 5 is 25. And when I subtract 27 minus 25, I'm left with 2. We can add on decimals if we want decimal answers, but typically at this point, what you would do is you would refer to the answer up top as the quotient and the number left over down here as the remainder. The idea here is if you have 627 of something and you're dividing it amongst, 5 people, each person can get 125 of that thing, but you'd have 2 left over. In other words, 627 is equal to 5 times 125 plus this additional 2. If we went through this exact same process using 625 divided by 5 instead of 627 divided by 5, our setup would be essentially the same. We'd write the 625 underneath this symbol with the 5 on the outside. Our goal would be to kind of get rid of this column as best we can. So we throw a 1 up top, and then we take this 1 times this 5 and multiply it by 5. And you can talk about why you're doing this multiplication and why in the next step you're doing subtraction. But I think for the purposes of this video, it might make more sense to just kind of memorize the operations that you do. So we're always multiplying this times this to get the 5, and we're subtracting 6 minus 5 to get this 1. Bring down the 2, we got a 12. If our goal is to get rid of as much of this 12 as possible by putting a number up top that'll get multiplied by this 5, the number we should put up top would be a 2, because 2 times 5 is 10, and 12 minus 10 is 2. Bring down the 5, we get a 25 down here, throw a 5 up top, 5 times 5 is 25. We end up with the remainder of 0. Really, the purpose of redoing this example with a slightly different number is to make the comment that when you have a remainder of 0, things work out kind of nicely. I can write an equation a lot like I did up here, where I say 625 is equal to 5 times 125, but now the number that I'm adding on at the end would be a 0. In other words, 625 is evenly divisible by 5. It's just 5 times 125. This will end up being kind of a special case that we want to think about when we deal with polynomial long division. So I wanted to show it to you with long division. Hopefully that wasn't too much of a waste of your time and it kind of reminded you of some stuff that maybe you knew in the past. Let's see if we can use that same algorithm to do polynomial long division. So now instead of taking 627 and dividing it by 5, I'm taking x cubed plus 6x squared plus 11x plus 8 and dividing it by x plus 1. So think, playing the role of the 627 is this long polynomial, and playing the role of the 5 is this x plus 1. Well, the way I set things up over here is I took the number down on the bottom and put that on the outside of this little symbol. So I guess I could do the same thing here. I could put x plus 1 on the outside of this symbol, and then on the inside of the symbol is this 627, the thing up on the top. Well, the thing up top here is x cubed plus 6x squared plus 11x plus 8. Things will be a little bit different down here because we're dealing with polynomials instead of numbers, but I think we can use the same overall strategy that we used up here. If you think about what we did up here, either in green or blue, our goal was to work from the left to the right, getting rid of as much of the leftmost column as possible. So we kind of looked at this 6 and wanted to get rid of it, so we put this 1 up top. It's the same idea down here. I want to get rid of this x cubed. In fact, unlike with numbers, with polynomials, we'll always be able to get rid of one column at least at a time. So the question becomes, what number should I write up top so that I can get rid of this x cubed? Well, whatever number we write up top, 1 in this case, we multiplied it by a 5 to get the number that we write underneath this 6. So analogously, whatever I write up here, I'll multiply by x plus 1 to get a polynomial that I would write down below here. If I want to get rid of this x cubed, since I know I'm going to subtract in my next step, I better end up with an x cubed right here. So how am I going to end up with an x cubed right here? Well, I guess I'd have to put an x squared up top. Why x squared? Because x squared times x plus 1 leaves me with x cubed plus x squared. This x cubed plus x squared is a lot like the 5 that I have written here. After I wrote this 5, I subtracted, so after I write this x cubed plus x squared, I'm going to subtract. Sometimes it helps to write parentheses around here to really remind yourself that you're subtracting all of this stuff. X cubed minus x cubed is just 0. I don't even need to write anything. 6 of these x squareds minus 1 of these x squareds leaves me with 5 of these x squareds. This 5x squared is a lot like this 1 right here. After I figured out this 1, I took the next column, a 2, and brought it down. I'm going to do the same thing here. I've got this 5x squared. My next column is 11x. I'm going to bring down that 11x. It's a little bit confusing when you're dealing with polynomials, but the good news is if you can get this far, you're good, because all we're going to do is repeat those exact same steps. Our goal is to get rid of the leftmost column. Instead of the leftmost column being x cubed, now the leftmost column is 5x squared. So I got to ask myself the question, what could I write up top so that when I take that thing and multiply it by x plus 1, I'll be left with 5x squared plus something else? Well, the answer to that question is just 5x, because the 5x times the x leaves me with 5x squared. But I'm not done here. The 5x also has to get multiplied by the 1, and that leaves me with 5x right here. And now I'm at the stage where I subtract. Again, to really make clear what I'm doing in my work, I'm going to write parentheses and put the minus sign up here, but that's kind of optional. You don't have to do it that way if you don't want. 5x squared minus 5x squared, the x squareds cancel out. 11x minus 5x leaves me with 6x, and I bring down the next column. I got an 8. I repeat one more time. I'm trying to get rid of this 6x. I ask myself the question, what do I got to write up here so that when I multiply it by x plus 1, I get a 6x down here? Well, the answer would be 6, because 6 times x leaves me with 6x. The 6 times the 1 leaves me with 6, and I subtract. The 6x's go away. 8 minus 6 leaves me with 2, and I'm done. I know I'm done because the degree of this polynomial, which is just 0, is less than the degree of this polynomial, which is 1. But in our class, this will always be linear. It'll be x plus or minus something. So we're done when this is just a number, doesn't have any x's in it left. We refer to the polynomial up top, x squared plus 5x plus 6, as the quotient. And we refer to this number down here, the 2, as the remainder. What the quotient and the remainder tell us here is the same thing the quotient and the remainder told us up here. It tells us we can take this polynomial, x cubed plus 6x squared plus 11x plus 8, and write it as a product of x plus 1 and x squared plus 5x plus 6 if we add on this remainder at the end, this positive 2. In case you didn't follow that, let me redo it one more time with essentially the same numbers. I'm just going to change this 8 into this 6. If you want, you can pause the video and see if you can do this polynomial long division by yourself. As a hint, the remainder should end up being equal to 0. The way you do it is you take the long polynomial that's up on the top and you write that underneath our long division sign. And you take the polynomial down on the bottom, which will always be linear in our class, and you write that out on the outside here. Now our goal, informally speaking, is to get rid of one column at a time, working from left to right by writing numbers up on the top, multiplying them, and subtracting. So the number that I'm going to write right here is x squared, and that's because x squared times x plus 1 leaves me with the x cubed that I was looking for. It also leaves me with an x squared, and I subtract. This column goes away. This column I'm left with 5x squared, and I bring down the next column. Now all I'm really doing is repeating. I want to get rid of the 5x squared, so the number I write up top is 5x. Why 5x? Because 5x times x plus 1 gives me 5x squared plus 5x. And importantly, I've gotten rid of this column right here. How have I gotten rid of it? Well, my next step is to subtract, and 5x squared minus 5x squared is just 0. In this column, I got 11x minus 5x, so I got 6x. I bring down the 6. I try to get rid of this 6x right here, so I toss a 6 up top. But when I put this 6 up top and multiply it by the x plus 1, I get 6x plus 6. So kind of coincidentally, or accidentally, I've not only gotten rid of this column, but I've also gotten rid of this column, because when I subtract, I'm left with 0. A remainder of 0 is really important because what a remainder of 0 tells you is your polynomial x cubed plus 6x squared plus 11x plus 6, in this case, can be written as x plus 1 times x squared plus 5x plus 6. Essentially what I'm doing is I'm taking the unfactored form of a polynomial and I'm writing that as a product of two polynomials. I'm beginning to factor this thing. I'm not done, it's not completely in its factored form, but we can get there fairly easily because x squared plus 5x plus 6 factors. We don't have good methods of factoring third-degree polynomials, but we're pretty good at factoring second-degree polynomials. If this is going to factor, I need to find two numbers whose product is 6 and whose sum is 5. Two numbers that multiply to 6 and add up to 5. Let's see, positive 2 and positive 3 will work. So x squared plus 5x plus 6 factors to x plus 2 times x plus 3. So my original polynomial, x cubed plus 6x squared plus 11x plus 6, in its factored form, is x plus 1 times x plus 2 times x plus 3. Now that I have the factored form, I could use the methods of the previous section to graph this guy if I wanted to, or answer any of the questions from the previous section. It's a long process and it's kind of confusing, and I've shown you the steps out of order, so maybe before I end this video, I can walk you through this entire process in order that you would actually do them if you were given this as like a test problem. So if I gave you the polynomial x cubed plus 6x squared plus 11x plus 6, and you wanted to sketch a graph of that polynomial without using any graphing software at all, you'd be thinking, well, I need the factored form. The way you'd go from the unfactored form to the factored form is first you'd list all the possible rational roots of the polynomial. So remember, possible rational roots are factors of 6, which are 1, 2, 3, and 6, divided by factors of 1, factors of the constant term divided by factors of the leading coefficient. Well, the only factor of 1 is just 1, so that ends up being pretty easy. I take any of these numbers and divide it by any of these numbers. There's only 1, and what I get from my possible rational roots are plus or minus 1, 2, 3, and 6. If there's a number that can be written as a fraction that's a root of this polynomial, it must be one of these 8 numbers. These are not all roots of this polynomial, they're just the possibilities for rational roots of this polynomial. From here, what we need to do is find one actual root. We don't need to find all of them, we just need to find one. So think there's 8 numbers and I'm going to plug them into this polynomial. Maybe I'll write it in function notation. F of x is equal to x cubed plus 6x squared plus 11x plus 6. I'm going to take these numbers, I'm going to plug them in, and I'm going to see if 0 comes out. If 0 comes out, I have a root. If anything other than 0 comes out, I don't have a root, and I don't even care what comes out if it's not 0. Which numbers should I plug in? Well, if you're a little bit clever, you might not plug in any positive numbers at all. Because if you change all the x's into any positive number, each of these 4 terms will be positive, and there's no way you're going to get to 0 by adding up 4 positive numbers. So I've kind of cut my list of 8 possibilities in half. There's really only 4 that might work. Let's try -1 just because that's the smallest number and that might make it easiest to calculate. -1 cubed plus 6 times -1 squared plus 11 times -1 plus 6. My question is that sum equal to 0? Well, let's see. This is -1. -1 squared is +1, and +1 times 6 is 6. 11 times -1 is -11, and then we have this 6 right here. On the positive side, I got 6 and 6, so 12. And on the negative side, I got -1 and -11, so -12. -12 plus +12 is equal to 0. When I put -1 into this machine, 0 comes out. So if I'm just looking for one actual root, I could say that x equals -1 is a root of this polynomial. You could plug in more numbers to find more roots, but you don't have to. From that one actual root, what you want to do is find a factor. So if -1 is a root, then x plus 1 must be a factor of this polynomial. Because if x plus 1 is a factor of this polynomial, and you set the product of all those factors equal to 0, you'd have x plus 1 equals 0, you'd solve and you'd get x equals -1. So because -1 is a root, x plus 1 must be a factor. Because x plus 1 is a factor, that means it must divide evenly into this polynomial. So if I take my polynomial, x cubed plus 6x squared plus 11x plus 6, and I divide it by x plus 1, I already know that I'm going to get no remainder here. Let's see how that works. My goal is to work from left to right, getting rid of one column at a time. I want to get rid of this x cubed. I do so by putting an x squared up here because I know I'm going to take this x squared and multiply it by x plus 1. And when I do so, I get x cubed plus x squared. And since my next step is to subtract, I can see that this column is going to go away. In this column, I again have 6x squared minus x squared, so I got 5x squared. And I bring down the next column, the 11x. Now all I got to do is repeat that a couple of more times. To get rid of this 5x squared, I put a 5x up here because 5x times x plus 1 gives me 5x squared plus 5x. And now I subtract. 11x minus 5x leaves me with 6x. And if I bring down this 6, I get 6x plus 6. And as we saw before, by putting a 6 up top, my algorithm tells me to take the 6 and multiply it by the x plus 1, and I'll get 6x plus 6 as the product, which when I subtract that from this 6x plus 6, leaves me with the remainder of 0. That's a good little check. I know that I had to have a remainder of 0 because I know x plus 1 is a factor. And if x plus 1 is a factor, it must divide evenly into this polynomial. There must be a remainder of 0. It's really easy to make an arithmetic mistake when you're going through here and doing this algorithm. But the good news is there's this built-in check. If you don't get a remainder of 0, go back and double check your work and figure out what went wrong. But I did get a remainder of 0, so what that tells me is that my original polynomial, x cubed plus 6x squared plus 11x plus 6, can be written as x plus 1, the factor that I found, times x squared plus 5x plus 6, the quotient when I did polynomial long division. The advantage of writing it this way is now I have a first degree polynomial and a second degree polynomial instead of a third degree polynomial. And the big advantage to having only first and second degree polynomials is I know how to factor second degree polynomials to make them first degree polynomials. As we saw above, x squared plus 5x plus 6 is just x plus 2 times x plus 3. So what we've managed to do is take our unfactored form and write it in the factored form by following through all these different steps. Now that we've got the unfactored form and the factored form, it's really easy to figure out things like the y-intercept, which would be 6 for this 6, the x-intercepts, aka roots, which would be -1, -2, and -3, coming from these three different factors right here, the end behavior, which is completely determined by our leading term, so positive 1x cubed, that tells me that as we go to the left, the graph goes down, and as we go to the right, the graph goes up. With these pieces of information, I could sketch the graph, and I'd be done with the problem. Looks like I didn't leave myself axes to sketch it, but that's okay. I can toss a 6 up here. I can put -1, -2, and -3 here. Note that the multiplicity of each of these roots is just 1, so my graph's going to go right through at all those different points. And since I go down when I go to the left and up when I go to the right, the graph, loosely speaking, is going to look like this. It's a long process, but it'll be the same process every single time you do one of these problems. So what I'll do in the next video is just repeat this process over and over again, give you a bunch more examples, but rather than try to teach you how to do it or explain why it works, just go through the process without any other context to get you a lot of different repetition so that this stuff becomes second nature. But I'm going to save that for another video and end this one here.